Swayam Prabha. Digital India. Educated India.
Our country is now at a stage where we need people in all professions. Okay, so whatever you do, should do your best. One, very good. One, two. Anybody else? Anyone else? And engineering? Very good. And sciences? There are two. Sciences also, there are different sciences, of course. Mathematics? Who is interested in mathematics? And who is interested in literature? Literature, languages, literature, fine arts. Fine arts. And then law? Law. Today we need good lawyers and judges, man. This country needs good lawyers and honest lawyers and good honest judges. You have to manage the 130 crore people. Only judges and lawyers only can save these people. How many of you will become lawyers and judges? No? None of you? Politicians? How many want you? If you want to go for political side, politics? How many you will do here for everything you are ready to do? Huh? After 15 years. So you have time. They don't record this. The sample and the IGNOU coming here, photon and the electrons coming out. These electrons enter here. They pass through the analyzer and then there is a detector here. That is a whole setup inside the spectrometer. Okay. So let me skip this and come here. As I said, all these lines are X-rays. They come here. They ionize these atoms. The light blue atoms are on the surface, and the dark blue atoms are in the bulk. So these X-rays come and they ionize electrons from these atoms, and they also go and penetrate into the bulk. A few micrometers they penetrate, and they also ionize the atoms here. So electrons come out here. See, these electrons are coming out. But these electrons, when they are passing through to reach the surface to escape, they'll undergo collisions here. Collision means they have to interact with the electron cloud, surrounding electron cloud. They lose kinetic energy. So they will not come out with the true kinetic energy. They lose kinetic energy. So the kinetic energy will be less compared to the kinetic energy to which they have come out. Whereas electrons which are ionized here, they directly escape into the vacuum, into the outside, and the kinetic energy is preserved.
Sir, when it goes to the lower layers and it comes back up, you're saying it loses a bit of the kinetic energy because of the collision. So, will the cations at the outer surface now attract and take those electrons and become atoms again?
Yeah. So, the ionized thing immediately will get neutralized. They get neutralized. Otherwise, you will end up having a positive charge. You are right.
So, they won't come out at all.
The surface, when it is ionized, it actually order of 10 to the minus 16 seconds ionization takes place, and immediately it will neutralize also, because it's a conducting sample. It's a conducting sample. So immediately the electron flows. Right? Okay. All right. So that effect will be very, very almost you can neglect that. Now what it is telling you is that the electrons which are coming from the surface are the ones which have a true kinetic energy. Those are the ones which gives you the actual peaks. And these electrons which are coming from below will give you background. So they form noise, background basically. Okay, let me show you that. So this is the spectrum. Now you see here, there are some electrons here. You see, these are all electrons. This step. Those are electrons which have lost some kinetic energy. They are coming from bulk and so they form a background, over which the electrons which are coming from the top layers form the actual peaks here. Okay, all right. Which means it is sensitive to surface layers only. This is sensitive to only surface layers. All right. Now, this is the EF. So we start measuring the binding energy EF. I told you the EF earlier. So this is the EF as a reference point. You start measuring the binding energy. Opposite is kinetic energy. Opposite is kinetic energy. Okay. So in the spectrometer, you can tune. You can actually set the spectrometer either binding energy mode or kinetic energy mode. So if you say spectrometer, I want spectrum to record in the binding energy mode, it will record. You say, spectrometer, I want it kinetic energy mode, it will record kinetic energy mode. Normally, binding energy mode is the one which people record. But these both options are possible. But modern spectrometers may not have both, I think. All right. Now, let's go to the next one. Yeah. So binding energy increases from right to left, and the kinetic energy is from left to right. Here, this one. So this is how the spectrum looks like. Crude spectrum, X-ray photoelectron spectrum of a solid surface. Solid. It can be metal, it can be it is a solid. Okay. Quickly we will go. Think I will skip this. I will come to this one. So here, this is the actual spectrum recorded spectrum of gold sample. Okay. So the X-ray uses magnesium K alpha X-ray, that is 1253.6 electron volt, the EV X-ray beam. Okay, all right. Now, so you can see this is the background. You can see that it's called inelastic scattering background electrons. Now, over that, you can see these actual peaks coming from different energy levels. For example, here gold 5p, here gold 4f, gold 4d, gold 4p, and gold 4s. Those are the peaks which belong to those particular electrons, which are superimposed on the background. Okay, all right. So this is an interesting thing. So this is the spectra. These are the spectra which are important. Remember here, this is very intense, this is less intense, etc. This intensity is something to do with the cross section. Cross section means the ionization cross section of that particular element, that particular energy level. Okay, all right. So if you wanted to analyze gold, if you want to see whether gold is there or in a sample, normally what they do, they take this is called 1000 volt scan. They take 0 to 1000 volts here. Full scan they will take, and then they start, suppose say you want to analyze a gold, you can actually record in this region here, which gives you very intense 4F, right? So that will tell you the story of gold which is sitting in the sample. Is it gold 0 or gold +2 or what is it? All right. So once you analyze this, you know everything about the gold atom sitting in the sample. You don't need to worry about all of them. Sometimes you can even look at this also, no problem. Okay, all right. So I'll just show you some examples. This is aluminum foil. You see aluminum foil. You see here aluminum. Aluminum has a lot of contamination. Oxygen, carbon, oxygen. These are oxygen 1s electrons. This is oxygen 2s electrons. This is carbon 1s electron. So it has a lot of contamination. That means surface of aluminum in the oxide form. Oxygen is there, a lot of oxygen is there. Okay, I'll just quickly tell you that thing. So somebody asked about OJ, right? You see here, this is magnesium K alpha, this is aluminum K alpha, and then OJ region comes at the same value, see around 800, you see that? These are OJ peaks of copper. OJ peaks of copper. They come around the same value, around 800 in this region. Whereas here, yeah, this must be copper 2p. Copper 2p comes here around 300, here around 400 to 600, this is 200 to 400. Copper 2p gets shifted because of the, you change the source, magnesium to aluminum. You see this copper 2p comes here between 400 to 600 region, and this is 200 to 400 region. You see, this is coming at different value. So that is how we distinguish OJ or X-ray photon. Okay, all right. This was recorded in 1988 using that machine I showed you. No, that was a machine used to record this. You can see. Now you will have very sophisticated Raman spectra. See, that's what I am saying. Here, you see this is OJ and this is OJ. You see the energy here? This is around 800 in this region. The same thing it is coming here. Even if you change the X-ray. But whereas this one is coming 600 to 500 to 600. And here it is coming 300 to 400. The shifts because the HNU is changing. That is how we distinguish the OJ or X-ray electrons coming from the, yeah. I mean, OJ electrons or photoelectrons. That is what you are distinguishing. Is it OJ electron or photoelectron? Okay, I just skip this and then I just give you one example of this. If you see, 1 second, let me go back here. You see, these 4f electrons have two peaks here. 4d have two peaks, 4p have two peaks, but 4s has only one peak. So the peaks are splitting. That splitting comes from, if you see, I will just skip this one and go here. Initially, in any orbital, you have two electrons, one spin up and one spin down. Total spin is 0. Now, if you actually remove this electron, photoelectron, by photoionization, either this can be removed or this can be removed. So, let us say this is removed, so you have this electron sitting there. Now, if you remove this electron, this has a L value. For example, if this is coming from p orbital or d orbital or f orbital, it has a L value, and S value is going to be only plus of or minus of, right? So, when you remove this electron, this remaining electron will combine the spin angular momentum of this combines with the orbital angular momentum of this level. L and S they combine, gives you two states in the two final states. So that's what is given here. You see. So the L orbital angular momentum, spin angular momentum. If you combine these two, L plus S, that will give you a J quantum number, which will have two values in the final state, right? So that gives you two peaks, and those are the two peaks here. So 3 by 2 half. This is for p electrons. Okay, the L and S they combine, give you two final states, right? So if there is no spin orbit interaction, that is one is spin, no, this is spin, that is the orbital angular momentum. So spin orbit interaction will take place. That interaction gives you a new energy level, new J value, new orbital angular momentum, total angular momentum, I would say. So the total angular momentum is L plus S now. Suppose say if you remove, so the S value can be either plus or minus. So if it is plus, you get L plus S. If it is minus, it is L minus S. So that will give you two final values. So that leads to two different peaks. So that's why if P is there are two peaks, and then the intensity of this is related to degeneracy. Degeneracy is something like a level, same energy level, same energy but different wave functions. Probably you are not. Are you familiar with wave functions? No, not yet. Right? Okay, all right. Don't worry about that. No. So there is, see, if this J value, if you substitute it here, you get two different. J is equal to, see, L plus S. I don't know where I have given. Yeah. L plus S, 1 plus half. How much? 3 by 2. Here. L minus S, half. 2 J values. Now that J you substitute here. Half you will get 2, right? Otherwise it will get 4. So two different values. The degeneracy is high, degeneracy is low. So the degeneracy is proportional to intensity. Higher the degeneracy, higher the intensity. Higher the degeneracy, higher the intensity. That's why you see this 3 by 2 peak is more intense compared to half. So the P electron when you ionize, you get two peaks because of the spin orbit. Intensity depends on the degeneracy. Okay? If you have not understood it properly, then don't worry about it. Okay? All right? You will learn it later, no problem. Okay? I think I'll skip this. Similarly, if it is P or P L is equal to 1, here L is equal to 2, L is equal to 3, because D electron will have L is equal to 2. Huh?
Does the degeneracy have anything to do with eigenvalues?
To do with?
Eigenvalues.
Okay. So if you are familiar with eigenvalues, the eigenvalues of those states, 4 states are same. Okay, if you are familiar with eigenvalues, energy is eigenvalue, right? So there are 4 states. For example, in the 4 states, the eigenvalues are same. Energy is same. If energy is same, it is similar to this. For example, you have 2 electrons sitting in this here, here. So energy is same for both the electrons, right? But then the wave functions are going to be different. The wave functions are going to be different. Simply.
Sir, how does the angular momentum of the orbital or the electron in the orbital affect the kinetic energy of the emitted electron? Because the graph is only about the kinetic energy of the electrons received by the spectroscope, right? So, because of this change in angular momentum, why do we see that reflected?
Your question, if I understand correctly, is that how? Can you repeat the question?
Sir, since based on which electron is emitted, the angular momentum of the electron in the orbital changes.
No, the orbital angular momentum will be same. The spin angular momentum will be different. It is plus half or minus half. Right?
So the total angular momentum changes.
That is because of the spin can be half or plus half or minus half.
Yes, sir. So since that electron is still in the atom and the spectroscope is only reading the kinetic energy of the emitted electron, how do we see that reflected?
Yeah, the emitted electron is gone. Now in the final state, when it reaches the final state, you will have these two. Okay, so maybe you see, for example, you have a number of atoms there. Some atoms, you can have plus half going out. Some atoms can have plus going out. So the probability of going this 3 by 2 level is going to be higher compared to the half. You can understand that way. All
yes,
right?
sir. Got it.
Yeah. So similarly, here L is equal to 2, L is equal to 3. So L is equal to 2 plus half, 2 minus half, 3 plus half, 3 minus half will end up giving you doublets because of spin orbit interaction. Right? Okay. So points to remember: PDF peaks, there are doublets there, but S electron will not have any doublet. The reason also you see PDF for non-spherical symmetry. S orbital is symmetric orbital, right? So that is another reason why you will not have any doublets there. And L is equal to 0. So, there is either plus of or minus of, it is going to give you a single peak. You take a modulus of that, right? Now, the separation is due to spin orbit splitting. Now, the important point here is the spin orbit splitting of a core level is going to be same irrespective of where the element is present. The element may be present in a different compound, but spin orbit energy difference is going to be same. The difference is going to be same. And then the peak ratios of the core levels and different compounds are also same. In other words, the intensity differences are there, P, D, F orbitals, the doublets. The intensity difference also will remain same irrespective of where the element is present, in which compound the element is present. These are all fixed. Okay, all right. And then of course, the highest J value will have the lowest energy. That's because of the Hund's rule. Anyway, that's a different thing. Let me show you some examples. I think I'll skip all these. Where is that? Here. You see here, let's look at now the application of this, what we have learned. Now you see here, this is the compound. This is there are 4 carbon atoms here. These carbon atoms are surrounded by hydrogens here, and this carbon atom is surrounded with 2 oxygens and 1 carbon, which is surrounded with 3 fluorine. So all these carbons are essentially different. If you record a photo emission spectrum, carbon 1s, it is giving 4 different peaks. So how do we understand that? 4 different peaks. Now you see here, this carbon is surrounded by 3 fluorine atoms and 1 this unit. These fluorine atoms, are negative inductive effect. They attract electrons from carbon. So the delta positive charge is more on this carbon compared to any other 3 carbons. Right? Now if you want to remove 1s electron from here, you have to spend more energy. The binding energy of that electron is going to be little higher. That is why this peak, is coming at higher binding energy here compared to all other carbons. Okay, that is called chemical shift. That is called chemical shift. Now come to this carbon, second one. This carbon is surrounded by oxygen, and then this group. Okay. Now this compared to this carbon has less delta positive charge because it is surrounded by oxygen. Not as the inductive effect is not as strong as fluorine, right? So the delta positive charge here is lesser compared to this one. That means the binding energy is going to be less now. Okay, higher the positive charge, the electron get attracted to the nucleus more. So you have to spend more energy. So binding energy increases, right? So this will, with respect to this carbon will give you a peak which is smaller in lesser in binding energy compared to this one. See this, so this peak is related to this carbon. Okay. Now go to this carbon. Now this carbon is surrounded by hydrogens and CH3 and O. So the chemical environment is different here. The chemical environment is different from this in this carbon. The chemical environment is different in this carbon. They are not, chemical environment is totally different. Now here the CH3 is a positive inductive effect. It donates electrons. So the electron charge here on this carbon is going to be much less. The positive charge is much less compared to other 2 carbon atoms. So this binding energy is lower than both of them. See, this peak is related to this one. The last one is this carbon where this methyl group. So that doesn't have any, these are all hydrogens and one side is this one. So the delta positive is even lesser. So this comes with a much lower binding energy. So as you go from here to here, the binding energy keeps on increasing from this to this to this. Okay. You understand that now? That is called chemical shift in photoemission spectroscopy. This you have to understand. Is that understood all of you? No, not yet. Don't, it doesn't matter. Tell me if you have any doubt. So this is called chemical shift. This is called chemical shift. You can identify, normally what do you expect? You expect a single peak because everything is carbon and 1s. This is 1s electron, you are ionizing 1s electron, carbon 1s photoelectron spectrum of ethyl trifluoroacetate, illustrating relationship between the binding energy and chemical environment.
Sir, just this thing, like if an electron is removed from the valence shell, even though the number of protons remain the same only, right? So how does it change the interaction of the 4 electrons with the nucleus, and how does
because if you are removing the electron with the valence electron, you are increasing the charge or decreasing if you are removing electron, you are increasing the charge. If you are adding the electron, you are actually decreasing the interaction.
But the number of protons remain consistent and the 4 electrons experience the same thing.
No. Suppose you have an atom A, which is neutral, A0, and A plus, for example, you are removing electron, A plus, right? So that extra charge is coming from nucleus, and that is experienced by the electron, which is core electron. So its binding energy will change. Binding energy will change, right? So that is the point. Now the same point, if you see here, this is silicon 0. It is this is the silicon 2p. It is 99.15 binding energy here. But then you remove, you convert this to SiO2. Now this silicon is 4 plus.
Sir.
Silicon is 4 plus. Now the binding energy changed to from 99 to 103. It is increased by 4 electron volt.
Sir, sorry, small doubt. On the last slide, does it matter what other atoms are bonded to carbon? In the sense, will the first peak be fluorine and the carbon bonded to fluorine, and the second peak be, or will we be able to predict that? There are 4 peaks for the 4 carbons.
Yes,
right?
4 peaks. This peak is because related to this carbon, this peak is related to this carbon, this peak is related to this carbon, this peak is related to this carbon. Because the chemical environment are not same. This carbon is surrounded by 3 hydrogens and then this group, whereas this carbon is surrounded by these 3 fluorines. So chemical environment is different, right? That affects the charge on the carbon. If the charge is affected, automatically 1s electron charge binding energy will get affected. The same example here. See, in this case, you have silicon here, silicon 0, silicon 4 plus, SiO2, silicon 4 plus. So obviously, silicon 4 plus means that the extra 4 plus charge, nuclear charge, is now influencing the 2p electron. It is going to catch it more. So if you want to remove, you have to spend more energy. So the binding energy automatically increases. It's increasing almost like 4 electron volt. 4 electron volt it is increasing. Okay. So this is so when atom loses valence charge, the 0 to 4 plus, binding energy increases. Binding energy increases. Here electron is lost. But in this case, electron is not lost, but the charge, the charge present on carbon keeps on changing from here to this carbon to this carbon. That is also showed up in the spectrum. If that does not, nothing happens, then all these 4 carbons should give you a single peak, right? If all carbons are same, chemical environment is same, you should get a single peak. It is not so. Chemical environment is different. This is surrounding by different elements. So automatically that will change the charge on the carbon. Whereas in this case, the oxidation state itself has changed. Silicon 0 to silicon 4 plus. Oxidation state itself has changed. Okay. This is another example where you see this is a complex. Platinum is here, right? So this platinum is surrounded by these 2 groups here and then 3 chlorines. And you see here this is platinum 4f electrons. This is 4f 7 by 2 and 4f 5 by 2 doublet. Now look at this one. This binding energy is around 74. Okay. Now we remove 2 chlorines here, only 1 chlorine is here. Now the binding energy has shifted, should shift to lower binding energy or higher one? Lower. You see that? That is shifted to lower binding energy. And only platinum metal 0, it is even much lower, coming around 70. See, so chemical environment has a very strong influence on the binding energy. Very strong influence on the binding energy. You can see these 3, you can easily identify them. Okay. So if you have a compound, this kind of studies can be done. And it is possible to extract some information on the oxidation state and then the chemical environment around that atom which you are actually looking at. Right? It is possible.